back to here. Hello, everyone. I'm Huaishu Peng from Cornell University. So this time, I'm going to present you with another piece of work. But instead of focusing purely on 3D printing, this work focuses more on the design and the interaction aspect of 3D modeling. I present D-Coil, a hands-on approach to design 3D digital models. This work is in joint effort with Amit, Zoran, and of course my advisor, Fran of Guimbreti. At this venue, at this moment, I think it is very clear to all of us that the advance of 3D printing and fabrication technology are evolving and are going to change people's lives. We have just seen technologies that enable people to make embodied 3D printing bracelet, or 3D printer that can print soft and interactive object, or techniques can accelerate printing and design iteration speed. Yet, we are still missing one piece in this series of exciting technologies, that is, a more approachable way for novice people to design 3D models ready for fabrication. Needless to say that the CAD is the most versatile way for 3D modeling. However, the learning curve for using CAD system remains steep, and therefore, to create complicated shape requires a lot of practice and training. Also, since CAD design is mostly an on-screen activity, the fabrication and design process are two isolated procedures, and therefore there's no tangible feedback when users design doing the design as in the traditional craft activities. I think this is a long-lasting problem, and many researchers have been working on this. First of all, to enable novice people for CAD design, researchers have been worked on improving CAD UI and interaction with systems such as Sketch, Teddy, and Allow Sketch, just to name a few. Researchers also look into mixing design and fabrication activities. Willis et al. Brings the notion of interactive fabrication with constructible and depend as two examples focusing in 2D domain. MixFab lowers 3D design barrier with a mixed reality environment with a transparent display. Finally, researchers also look into digital-supported fabrication with examples such as computer-controlled aimed 2D router or computer-controlled aimed milling machine 3D. Different from prior art, we are looking into a fully explicit design approach to offer tangible feedback for novice users. Our inspiration draws from traditional clay coiling activity. Clay coiling has been used to create vessels for many thousands of years. When prepare a long clay coil, and by placing one coil on top of another, different shapes can be formed. Inspired by this, we present D-Coil, a 3D modeling system using wax coiling to bring tangibility to the design of 3D digital model. D-Coil centers on an augmented wax extruder, a wax cutter, a workbench, and a 6DOF mouse. Both our extruder and the cutter design derives from the 3D milling machine. Different from CAD system, D-Coil offers a hand-on approach to digital 3D modeling in the physical world. So in the next couple of minutes, I'm going to show you the interaction and operation supported with D-Coil. But now let's start with a toy example of designing a digital cylinder to get a sense of how D-Coil works. As in CAD system, digital models are designed by creating a succession of basic geometric primitives, but with D-Coil, additive construction takes place in the physical world. Thus, to design a cylinder, one would use a D-Coil extruder to define a 2D circle as the cylinder base. Then follows the lead of the actuated extrusion tool to coil up layers as an actuated physical version of the cylinder in wax. Because the model is instantiated in wax as it is created, design and construction happen at the same time. That, different from CAD, the user can actually touch and get a sense of the scale of the model through this tangible proxy. Also notice that the final output of the D-Coil design is the digital model, which affords all the benefit of the digital world, such as ease of modification, distribution, and replication. The wax model, on the other hand, is used as like one-time design proxy to give you the sense of the design process. Here's the way users design the cylinder. The user first designs a work plan, then define a 2D circle with its center and a radius. In the digital world, a 2D profile is created. The D-Coil extruder knows the position of the extruder tip and therefore can lead the user's hand's movement to extrude the regular shape by layers. After one layer is finished, the system can automatically guide the user to build a second layer in the physical world. And in the digital world, the 3D model height will be updated as well. The building process keeps going until the user is satisfied with the height of the cylinder. Then the user finishes the design. Here we can see the result of the simple cylinder example. On the left is a 3D printed cylinder from our digital model, which is generated by the building process of making the middle wax cylinder proxy. You can see that the digital model and the physical model are almost identical to each other. Finally, as a comparison, the red cylinder is built without any actuation mechanism. With this basic extrusion tool, the user can start simple designs examples like this candle holder shown here. Of course, 3D modeling is not just about adding things. Users also need to find a way to cut, and therefore we include a computer-controlled cutter into the D-Coil toolbox. Like the extruder, with a cutter, the user first defines the cutting profile, then follows the actuation lead to finish cutting. Here is a castle example with a rampart and a gate designed with a cutter. So far, our 3D modeling is mostly based on simple extrusion. This certainly limited the model complexity. For example, a teapot would be not possible with this kind of simple extrusion. To make D-Coil system more applicable, we revisit the common clay coiling practice and observe that the craftsman actually achieve complex 3D shapes by layering 2D profile with different shapes on top of each other. This inspired us to use a 6DOF mouse to locally control the 2D shape of each of the layers for the coiling. With the 6DOF mouse, the user can use this non-dominant hand to have the control of each of the layers of the 2D profile to create translation, scale, rotation, or tilt. Here is a couple of results created with a single 6DOF mouse operation. Having the control of each of the 2D profile transformation have greatly improved the design expressiveness, but there are some examples that are difficult in this method. For example, it would be difficult to create this picture lit only with this local transformation. To tackle this, we extended this D-Coil toolbox to enable the user to add the 2D profile during the construction of the 3D model. Here we explore two operations. The first one is a split. It allows user to split a 2D profile into several individual ones and edit each of them separately. The second operation is override. The user can override a 2D profile to integrate it into the original one. This video clip shows the user extrude a cylinder and then cut the circular profile into two pieces. Then only worked on one side of the circle. As we said earlier, Comparing to traditional craft techniques, one of the advantages of D-Coil is that it enables fast replication with a copy and paste feature. This is extremely useful when the models have repeated geometries like the example in here. To copy a part of the model, the user can draw a copy guideline along the part of the model to be selected. And to paste the selected model, the user points this tool at the target location and then decide if she wants to instantiate this copy physically or purely digital. Now I'm going to show you a couple of examples designed with our D-Coil system. In this example, the glass frames are created using the copy and paste function. And the instantiation of this copy happens in both digital and physical world. The armor of the glasses, however, only paste digitally but not instantiated in the physical world. The lip of this picture is made by overwriting the base profile. This is a teapot we made with D-Coil. The body is built with a scale up and down function, and then we have the cutter hole out of teapot body. And then we extrude the sprout with another scale and tilt method. We finally made the handle with a freehand drawing function supported with D-Coil. This is a house example designed to start from a 2D rectangular shape. They extrude up vertically, then scale down to create the roof. The window and the door is made possible with the cutting tool introduced previously. This pen holder is made by splitting the base profile into two and extrude each of them individually to two different directions. Finally, D-Coil could help design 3D models fit existing objects, something difficult for pure CAD users. In this example, we design a small crawl for this frog. And to do so, we simply trace the contour of the frog head. We then extrude it for several layers and build other components on top of it. Now I want to have a brief discussion of the observation and lessons we learned during the design of the D-Coil system. First, design speed. We understand that the physical instantiation is not a fast process, and therefore our current prototype attempts to solve this by introducing the active guiding to lead users for the construction process. We have anecdotal evidence that the actuation itself can provide a fourfold increase in speed when compared to an off-the-shelf extruder. Also note that the work presented here is just a lab prototype, and the speed can be further improved with a more sophisticated mechanical redesign. Next, we would like to talk about the material. Drawing inspiration mainly from the clay coiling, our exploration actually started with the extruding clay. However, during our preliminary test, we discovered that clay ribbon is too easy to break and take too long to dry. We also considered plastic wires like ABS or PLA, but they also pose challenges for cutting because they were fairly rigid after they get cured. We finally opt for wax wire because of its low melting point, fast cooling, and ease of cutting. We think that D-Coil has demonstrated great expressiveness with an explicit design approach. However, there are models that require more than purely explicit design. For example, this boat hull design are often represented as a series of sections along the main axis of the boat, and therefore need inexplicit design or common-based design support. This would certainly be a future direction of our D-Coil system. We have shown in our last frog crawl example that the D-Coil system could be used to create models with good fit to existing objects. We believe that this feature could be further extended so that the D-Coil could be used as an in-situ fixing tool. Finally, we intend to implement a more robust D-Coil prototype for broad development and evaluate it with both novice and expert coilers. As a conclusion, we present D-Coil, a digital modeling system using wax coiling to bring tangibility to the design of the digital model. Combining with an extrusion tool, a cutting tool, a 6DOF controller, the user can create a wide variety of digital models in a reflective design manner with timely physical feedback. Our work is supported by NSF award and in part by Microsoft Research. And now I'm ready for your questions.
Anthony Hornoff, University of Oregon, great work. Given that you have the active guidance, why do you use a human arm? Why don't you use a robot arm?
That might be possible, I guess. But with a robot arm, you will lose the chance to actually feel the things with your hand.
Okay,
right?
So there's a benefit to the user to learn the form.
Yes,
okay,
I think so.
Thank you.
Hi, Daniel Ashbrook from the Rochester Institute of Technology.
Hello.
I'm curious how you're actually tracking this thing as you move it around.
Right. So I kind of skipped this part because our system is based on previous work with 3D. So the tracking mechanism is used a 6DOF magnetic tracker. It's a tracking source located at our workbench. And the tracker is attached to the extruder so that at any given moment it can know the tip location.
Thank you.
Sure.
I have one question. Could you use that as some sort of a scanner to augment any arbitrary object? So maybe I have a weird phone from which I don't have any 3D model of, and I want to just design a freestyle case for the phone. Could I use that? The tracking fidelity, is it good enough to actually scan the surface of the phone and then actually use it for 3D printing?
I think this is a really good question. I don't have a full answer for you, but based on our experience with this tool, for example, building this crown fit, this not even top surface of the frog head, I think this is really possible.
Cool. Thank you.